Okay, let's picture this. The very, very early universe. Just
Darkness.
right.
Mind-boggling.
Utterly. And for so long, the huge question has been, well, how did the lights come on? How do we get from that primordial gloom to, the stars and galaxies we see?
What was that first spark?
It's this epic cosmic mystery, really. And now, thanks to the James Webb Space Telescope, the JWST, we're getting some seriously interesting new clues.
Yeah, I saw that. There's a new study out in Nature, isn't there? It seems like it's really shaking things up a bit.
It really is. It's challenging some long-held ideas about that whole era, the time the first light emerged.
Right. So we've been digging into this research, looking at how scientists have tackled this puzzle of what they call cosmic reionization.
Exactly. And for years, the thinking was, well, it must have been the big players, right? The really massive, bright galaxies, maybe supermassive black holes, the heavy hitters.
Makes sense, intuitively.
Yeah.
But this new study seems to point somewhere else entirely, maybe an unexpected hero in the story. That's precisely it. Our deep dive today is all about this new evidence. It suggests a pretty surprising source for that first light.
So we're going to explore how JWST managed to look that far back. It's credible, and potentially found these sort of unsung heroes.
Yeah, using some really clever cosmic tricks to see things we just couldn't before.
Okay, let's start there. How can you even see that far back? It sounds almost impossible, like spotting a match flicker across the country.
Ah, that's a good way to put it.
Yeah.
Well, the key technique here is something called gravitational lensing.
Ah, lensing,
Right.
where massive objects bend light.
Exactly. You get these huge things in space like galaxy clusters, truly enormous structures,
Yeah.
and their gravity is so immense it actually warps space-time around them.
Like a lens.
Like a giant natural magnifying glass in space. It bends and, crucially, magnifies the light from objects far, far behind it, objects we wouldn't normally be able to see.
So for this study, they used a specific cluster.
They did. They focused on a galaxy cluster called Abell 2744. It acted as their cosmic telescope, letting JWST peer into the very early universe behind it.
Okay, so they used this natural lens to zoom in. And what did they find? Did the usual suspects, those massive galaxies, not quite fit the bill?
Well, that's the twist. The data seems to show that ultra-faint dwarf galaxies played a huge role, maybe the key role in kicking off the cosmic dawn.
Dwarf galaxies. Wow, so not the big bright ones, but these tiny ones.
Much smaller, much less luminous than the ones everyone previously thought were responsible.
That really is a plot twist, isn't it? The entire universe going from dark to light, and it's potentially down to these little guys, seems counterintuitive.
It absolutely does,
Yeah.
and that's why it's such a big deal. There's a quote from Irina Chemerinsky, an astrophysicist at the Institut d'Astrophysique de Paris.
What did she say?
She basically said this discovery shows the crucial role these ultra-faint galaxies played, that they produce these things called ionizing photons.
Ah, ionizing photons. Those are the key, right? The high-energy light particles that can knock electrons off hydrogen atoms.
Exactly. They're what essentially cleared the fog. Before reionization, the universe was full of neutral hydrogen gas, which is like a thick fog for light. It absorbs it. Opaque.
So these photons zapped the hydrogen, made it transparent, and let light travel freely.
That's the idea. And these dwarf galaxies, despite being faint individually, seem to have been incredibly efficient factories for producing these ionizing photons.
Okay, hold on. If they were so effective, why did everyone focus on the massive galaxies and black holes for so long? What was the logic there?
Well, it was partly observation bias, perhaps. Those are the brightest, most energetic things we could see easily in the early universe.
The obvious candidates.
Right. Massive galaxies have bursts of star formation, which should produce ionizing light. And supermassive black holes, when they're actively feeding, blast out enormous amounts of energy. It just seemed logical they'd be the main driver.
But the JWST data tells a different story. What's the specific evidence pointing to the dwarf galaxies?
Okay, there are a few key things. First, JWST spectroscopy is incredibly powerful. It can analyze the light from these very faint objects in amazing detail.
Like getting a fingerprint of the light.
Precisely.
Yeah.
You break the light down, see what elements are there, what kind of radiation they're emitting, and they saw the specific signatures of this intense ionizing radiation coming from these dwarf galaxies near Abell 2744.
Okay, so direct evidence of the right kind of light. What else?
Numbers. They found these dwarf galaxies were way, way more numerous than the bigger ones, something like 100 times more abundant.
100 times. Wow.
And then, the kicker,
Well,
when they calculated the total amount of ionizing radiation coming from all these dwarf galaxies
let
combined.
me guess. It was a lot.
It was 4 times more than the contribution from the larger, brighter galaxies they saw.
4 times. So
Yeah.
it's sheer weight of numbers plus this surprising efficiency.
Exactly. Each one might be small, but there were just so many of them. And they were churning out this specific type of radiation very effectively.
It's the collective power.
That's it. Hakim Atek, who led the research team, put it really well. He said these low-mass galaxies are prolific producers of energetic radiation, and that their huge numbers meant their collective influence can transform the entire state of the universe.
Cosmic powerhouses in disguise.
You could say that.
Yeah.
Despite their tiny size, they collectively had enough energy to, well, get the job done.
This really changes the picture of the early universe, doesn't it? It's like finding out it wasn't just a few giant spotlights, but millions of tiny LEDs lighting everything up.
That's a great analogy. And it has knock-on effects for how we think about other things, too. It's not just about how the lights came on.
Right. What are the broader implications then, if these little galaxies were so important?
Well, it makes you ask, how did so many of them form so early? Our models of galaxy formation might need adjusting. What were the conditions back then that favored making lots of small galaxies instead of fewer big ones right away?
Does it tell us anything about the first stars themselves? Were they different in these smaller galaxies?
That's another big question this raises. Maybe these dwarf galaxies had a higher proportion of really massive hot stars, the kind that pump out huge amounts of UV radiation, the ionizing kind. It could change our ideas about early star evolution.
Okay, galaxy formation, star evolution. You mentioned dark matter, too. How does that fit in?
Well, the standard picture is that galaxies form inside halos of invisible dark matter. The properties of those halos influence the galaxies.
So if you have loads of small galaxies,
It might imply something about how dark matter was distributed back then. Maybe it clumped in a way that created many more small halos, perfect nurseries for these dwarf galaxies, rather than fewer giant halos early on.
wow. So one discovery ripples out across cosmology. It really is, as the study says, a profound shift. These apparently minor objects having such a massive impact.
It is profound. It shows how sometimes the loudest or brightest things aren't the whole story. Collective effects matter hugely.
Okay, but this study looked at one patch of sky, right? Using Able 2744. Is this picture potentially just specific to that region?
That's the crucial next step. This is an amazing result, but it is based on one deep look through one gravitational lens.
So they need to check other areas.
Definitely. The researchers plan to use JWST to look through other cosmic lensing zones, observe other parts of the early universe, and see if they find the same thing.
To confirm if this is a universal pattern.
Exactly. Expanding the dataset is key to really cementing these findings.
It feels like JWST is just opening up a whole new view, doesn't it? Like we've been looking through a keyhole, and now the doors have been thrown open.
It really does. Damiya Nanayakkara from Swinburne University had a great quote on this too. He said, "We've entered uncharted territory with the JWST."
Uncharted territory. I like that.
And that this work opens up more exciting questions about, our cosmic beginnings. It's not just answers, it's new puzzles.
Which is what science is all about, really.
Absolutely.
Okay, so let's recap our deep dive here. The big takeaway seems to be, forget just the giant galaxies. These tiny, numerous dwarf galaxies look like they were the real engines of cosmic reionization, lighting up the universe way more than we thought.
That's the essence of it, based on this new JWST data. It seriously challenges those older assumptions about how the universe stepped out of the Dark Ages.
It suggests maybe it was more of a gradual dawn, powered by countless small sources, rather than a few giant floodlights switching on.
A more democratic cosmic dawn, perhaps,
Yeah.
driven by the collective effort of the little guys.
It really makes you wonder, then, if we were potentially wrong about something this fundamental, how the lights came on because we underestimated these small galaxies. What other basic assumptions about the cosmos might need a rethink as we keep pointing powerful tools like Webb at the sky? What else are we missing by focusing on the biggest and brightest?
That's the really exciting, maybe slightly unnerving question, isn't it? It feels like we're just scratching the surface. There are likely so many more surprises waiting out there in the dark.